Hello, I'm Kurt. Welcome again to Comp Sci 5. Today we are going to be talking about big O notation. And big O notation is just a big word that concerns itself with growth rates, okay? So before we talk about big O, let's just put some basics up on the board. Let's get the basics covered. Over here I have a graph on the board, and on the horizontal axis we have input size. On the vertical axis we have runtime. Now, as computer scientists, we all want to have fast programs. Everyone wants a fast computer. Nobody wants to be waiting for a web browser to load whatever you want to view. So we utilize Big O a lot in computation. So to start off, we have this first function, this horizontal line, and it's pretty much growing. As input size increases, runtime does not change. We call that a constant time. We'll denote it with a little c. And the next function that we have, the one that grows faster than a constant function, is a logarithmic function. We'll say log n. The one that grows next fastest is a linear function, n. The function that grows next fastest is quadratic, n squared. The function that grows next fastest, you guessed it, cubic, n cubed. And the one that grows fastest of them all is an exponential function, which is 2 to the n. Now, n factorial is also an example of an exponential function, but we haven't included it in here just so we have a more well-spaced out diagram that's easier to see. Let's take a look at what these runtimes are doing. Let's take a look at what these functions are doing in terms of their runtime. All right. So as we said before, we have our baseline function, the really cool one. We have our constant function, and that grows no faster than log of n. Log of n grows no faster than n. N grows no faster than n squared. N squared grows no faster than n cubed. And of course, n cubed grows no faster than 2 to the n. I keep saying grows no faster than because essentially that is all big O is really saying. That's all this symbol, which I'm about to introduce to you, says. So if we look up here, all these less than and equal to signs, we can just as easily erase them and put in a giant O. A big O, some would say. And so now we have constant big O of log n big O of n big O of n squared big O of n cubed, and of course n cubed big O of n squared. Great. So all big O is saying that the function to the left is growing no faster than the function to the right. That's all it is. If you want a precise definition, of course, Google it. So let's talk a little bit about the laws associated with big O. And the first one is very intuitive, very intuitive. It's called chaining components. Just to illustrate that for you, if constant function is big O of logarithmic function and logarithmic function is big O of linear function, then constant function is big O of linear function. That's just called chaining. Cutting coefficients is, well, I'll just draw out a little example. Let's say you had 2 n squared is big O of n squared. Basically, you cut this coefficient right here. It doesn't matter in the long run. Let's move on to the next one. Drop lower order terms. So another example for you. Let's say you had 4n squared plus 2n plus 1. What is that big O of? Well, we are going to drop these terms right here. Boom, boom. They no longer matter. We're also going to cut our coefficient, and you guessed it, it is also big O of n squared. So why do you care about all this? Well, big O notation is used to analyze programs in their runtime, which, because we're running out of time, we'll talk about next time on Comp Sci 5. Thank you for streaming in.